Your processor runs billions of operations every second, so here is something strange. Most of the time, it is barely doing anything at all. Right now, your computer is mostly waiting. Open the Task Manager, and you will probably see the processor sitting at just a few %. Out of every 100 clock cycles, only a handful do real work. The rest are spent doing nothing. And that is not a flaw. Being lazy is exactly how a modern chip stays fast and cool. To see why, we have to start at the very bottom. A processor is driven by a clock, a signal that ticks billions of times a second. One tick is one cycle, the basic heartbeat of the chip. At 4 GHz, that is one tick every quarter of a nanosecond. Inside, there are billions of tiny switches called transistors. On each tick, some of them may flip between 0 and 1. Here is the key idea. A transistor mostly burns energy at the moment it flips. If nothing changes, very little power is used. Engineers call this dynamic power, the power spent switching. So the chip has one simple goal: flip as few switches as possible. So what does a processor do when there is no work to do? It runs an instruction that literally means do nothing. It is called HALT. The operating system keeps a special idle loop whose only job is to run it. When the chip halts, it stops its own clock and freezes in place, spending almost no energy. It stays frozen until something needs attention. A key press, a network packet, a timer. That event is called an interrupt. The interrupt wakes the chip in a matter of nanoseconds. It does a tiny bit of work, and then it goes right back to sleep. On an ordinary desktop, this happens thousands of times every second. But a chip is not all or nothing. It is split into blocks. A core here, a math unit there, a cache, a decoder. At any moment, most of them have nothing to do. So the processor plays its first trick, cuts the clock signal to the blocks it is not using, right down to individual pieces of logic. No ticks means no switching, and no switching means almost no dynamic power. This is called clock gating, and it happens automatically, steered by tiny enable signals all across the chip. The power a block draws depends on its capacitance, its voltage squared, its frequency, and how active it is. Gate the clock, and that activity falls to 0. When a whole core has nothing to do, the chip goes further. It puts the core to sleep. There is a ladder of sleep states, from fully awake down to deep sleep. In the lightest one, the clock simply stops. Go deeper, and the core flushes its caches and saves its state. In the deepest state, the core is almost completely powered off, drawing only a trickle. The deeper the sleep, the less energy it uses, but the longer it takes to wake, from a fraction of a microsecond up to tens of microseconds. Your processor is constantly riding up and down this ladder, sleeping and waking thousands of times a second, far faster than you could ever notice. Now here is something that feels backwards. To save energy, the smartest thing a processor can do is hurry. Imagine the same task done 2 ways. It could run slowly and steadily, sipping power for a long time. Or it could sprint at full speed, finish quickly, and then drop into deep sleep. Energy is power multiplied by time, the area under the curve, and the sprint usually wins. Deep sleep is so cheap, and an idle core still leaks a little power just by being switched on. So finishing fast and powering down completely beats dragging the work out. Engineers call this race to idle. Do it fast, then do nothing. Sometimes the chip cannot just sleep, because there is steady work to do, but not very much of it. In that case, it uses another trick. It slows itself down on purpose. It lowers the clock frequency, and it also lowers the voltage. This matters because power grows with the voltage squared. So a small drop in voltage gives a big drop in power. This is called dynamic voltage and frequency scaling. The operating system adjusts these levels many times a second, choosing the lowest setting that still keeps up. Halve the speed when you do not need it, and you can cut the power by far more than half. The chip only reaches for its highest speed when you truly need it. So far, this has all been about saving power. But there is a second kind of laziness, one that shows up even when the processor looks completely busy. The problem is memory. The chip can do arithmetic in well under a nanosecond, but main memory is painfully slow by comparison. A value sitting in the fastest on-chip cache arrives in about 4 cycles. A trip out to main memory can cost 200 cycles or more. A modern core can start several instructions every single cycle, so one long wait can throw away hundreds of chances to do work. This gap between fast logic and slow memory even has a name, the memory wall. So even when it looks fully loaded, much of the time it is simply waiting for data. To avoid that long wait, the processor is lazy in a clever way. It refuses to fetch the same thing twice. When it reads a value from memory, it keeps a copy nearby in a small, fast store called a cache. The next time it needs that value, it is already there, just a few cycles away. We call that a hit. A miss means going all the way out to memory. Chips actually keep several levels of cache, a tiny fast one, then larger and slower ones behind it. Because real programs tend to reuse the same data again and again, the large majority of accesses are hits, often more than 95%. The cache turns slow memory into something that usually feels fast. There is one more way the processor avoids waiting. When the code reaches a branch, a decision about which way to go, it often does not yet know the answer, because that depends on a value still being computed. Instead of stopping to wait, the chip makes a guess. A branch predictor picks the most likely path and keeps right on working, as if the guess were already confirmed. It will even run instructions out of order, doing whatever is ready instead of waiting in line. This is called speculation. Modern predictors are right around 95 times out of 100. When they are wrong, the chip throws away the guessed work and tries again, paying perhaps 15 or 20 wasted cycles, a rare and cheap price for almost never having to wait. So your processor is not slacking off. It is doing the hardest thing in engineering, only the work that truly matters and not a switch more. It sleeps whenever it can. It avoids any work it can skip, and it would rather guess than sit and wait. The fastest work, after all, is the work it never has to do.